So in the previous class, so I will announce about the final exam. So actually, so we will take final exam the the last day. On the last day of the semester, it means that we will take the final exam on December 21st. Okay. And then, so as I mentioned, so we will take the final exam in this classroom. Okay. So then so I will post the logistics logistics of the information of the logistics of final exam on Blackboard. Okay. So yeah, this is similar to the bit here. Okay. Uh, in the previous class we learned about the cache, and then actually we learned about the direct mapped cache. So cache is the temporary memory that can store the frequently accessed data. But we don't know which data will be frequently accessible. So, actually, when the data is referenced, so which means that data is requested by load instructions or data is updated by store instruction, and it's called the referenced. Okay, data is accessed, and it is called data is referenced. So when the data is referenced and the cache is checked, and then the reference data is found and it's cached, it's okay. And then if the reference data is not found, it's cache missed. So in this case, the data is delivered to the cache from the low-level cache or memory. Okay. So when the data is delivered to the cache, one cache block. So I mentioned this byte offset is size the cache block size, right? Because so this figure shows that the size of the single cache block is 4 bytes, right? Because we just assign 2 bits of the address, 2 bits of address field. So it means the one cache block occupies 1 word is the 4 bytes. Okay. So when the cache miss occurs, then the entire block. So this size of data, and then the size of data is equivalent to the size of a single cache block. So this amount of size of block is allocated to the cache. Okay. So, and then I also mentioned that the lower part. So after this byte offset part, so and then we can find the cache index field. So it's a lower part of the address field. Okay. So we assign this lower part of the memory address as the cache index. Okay. And then we use the remaining part as the head. So I mentioned that we need to distinguish which data exists in cache or not, right? And then we can identify the target data using the address of the data, right? So instead, we need to store the address of the data, the cache also, but we don't need to store all bits of this address, right? Because we use the part of it as the byte offset, and then we also use the part of it as the cache index. Okay, and then we don't need to store these bits. So we just store the tag field, the remaining bits of the address. Okay, that's what we learned in the class. Okay. And let's think about the write operations in cache. So until now, so we discussed about the read operation on cache. But writing can be different because when the write operation is requested, the write operation is requested by store instructions, right? The write operation is requested, then we need to update the data, the target data in the main memory, right? So, but because we have cache memory, the target data can be found in the cache, or the target data can be found in the main memory, right? It can be found in the cache, or it can be found in the main memory, right? So, and the next, think about the situation that when the write operation is executed by a processor, then the cache is accessed, and then the write request hits the cache. So which means that the target data is found in the cache, right? It's just so small. It's a cache, and then it's main memory. And then for target data, so it's a cache block, and then we can find the target data in the cache. And the write operation is requested. So because the target data is in the cache, so this data is also in the main memory, right? The cache is the small memory, so it's a temporary memory, and then actually we can find the every data in the main memory, and then cache just stores the part of data in the main memory, right? So write request is given to the cache, then the data is found, and then it's write hit. It's also hit, right? It's a write hit. So this is called the write hit. But we need to distinguish how to update the data for this write hit case. What does that mean? What is the definition of a store instruction? The definition of a store instruction to transfer the data in register file to main memory. So actually this is the definition. So when the store instruction is executed, which means that the data in the main memory needs to be updated. But because the processor has cache, the same data is found in the cache, also found in the main memory. So what do we do? So there are two cases, right? The first case is that, so this is the definition of the write store instruction, right? So we need to update this data, right? So the first choice is that, we can update the data in the cache. Also, we can update the data in the main memory. Okay. So do you understand? Because this is the definition of the store instruction. So we need to update the data in the main memory. So the first choice is that we can just update the data in the cache, also data in the main memory. So for this operation, so actually this operation is called the write through cache. So for we can classify cache as the write through cache, and also we will learn about the write back cache. So we can just classify cache as the write through cache or write cache based on the write operation. Okay. So in the write through cache, and the write request is given, and then the write hit, and this is updated, and then the request is also given to the main memory, and then the data in the main memory is updated immediately. Okay. So this is the write through cache. Okay. Okay, what's the problem? So why we use cache? because main memory is slow. Write operation is the same. So until the write operation is completed, it will take long time in the main memory. So which means that when the write store instruction is executed, and then in the write to cache, so cache is updated, and also the write this main memory needs to be updated. So until this operation is complete, then the processor needs to wait. Because the definition of what I to do is that when the store instruction is executed, the main memory needs to be updated immediately. Okay? And then the problem is that main memory is very slow. So problem is that if we use the store instruction in our program, it will take very long time, right? And then you also if you read some compiled code, that you can find many store instructions, right? So it's not actually good. Then what is the solution? So in this case, the problem is that target component. This is the target component. The main memory is the target component, but the target component is very slow. Okay, and then so actually for the store instruction, we don't need to get any response from the main memory, right? So this is just the one direction command. So just update the data in the main memory. So we don't need to wait until we can get response from the main memory, right? So the target is so slow, and then so this is the one direction command. So in this case, we can use buffer here, right? So the write request also given to the main memory. So write request is issued. The write request is cache generate the write request. So this is called the issue sequence actually. So write request is issued by cache, and then this write request is stored in the buffer. Okay. So then if the write request is stored in this buffer, then the cache completes the write operation. So this buffer request will be given to the main memory in the future. Okay. So this is just the buffer. So in the main memory is idle, then the request will be given to the main memory. Okay. So we can use the write buffer. So this is the write to cache. So which means that for the write hit case, the write request is also given to the main memory immediately. Also, we can consider the second possible operation is the write back. So write back means that this is cache, this is the main memory, and then also this is the write hit case. The target data is found in the cache. So write back operation means that this is the write operation by store instruction. Okay. And then, so actually, if the data exists in the cache, right? If data exists in the cache, then this cache will provide data to the CPU, right? So if the data is updated in the cache, then this updated data will be also provided to the CPU if requested, right? So what does that mean? If if this data exists in the cache, we don't need to check main memory, right? So the store word some address A, the address A. So then if this A is in the cache, then if we execute the load word A, then this A will be provided by cache. So what does that mean? If data exists in the cache, then actually we don't need to update main memory. So I mentioned that if the target data exists in the cache, right? So write back cache means that for the write hit case, the write request is given, and then this is the write hit. Oh, this write the target data exists in the cache. Then only this cache line or cache block is updated and done. Okay. So what's the problem? The problem is that, oh, this is the store instruction. So by the definition of the store instruction, then actually we need to update the main memory. Okay. So actually store instruction need to update the main memory. But in the write back cache, and the store instruction is executed, and then if the data is found in the cache, so the data in the cache is only updated. Okay. So actually, so this is the store instruction, and then based on some definition by instruction set architecture manual, the main memory is to be updated, right? So when? So I mentioned that if data exists in the cache, right? So this data can be evicted from the cache because the cache size is limited, right? The cache size is limited. So in the future, this data will be evicted from the cache, right? Then, oh, this block is updated. So in this case, the cache gives the write operation to the main memory was the low level cache, the main memory. So the main memory is also updated. So write back cache means that if the cache is for the write hit case, and then write operation is given to the cache, then the only cache is updated. And then this updated block is reflected to the main memory until when the cache block is evicted from the cache. Okay. So which information is required in this case? So cache block. This is the cache block. Cache block can be evicted from the cache, but there are two cases. This block can be updated or not updated. So there can be two cases. So if the cache block is not updated, then this block is evicted, then you can just throw away this not updated cache block because it's the same. This data is the same to the data in the low level cache or main memory, right? So in this case, we don't need to, actually we can throw away this updated block. Not updated block. So not updated block. But if the block is updated, then this block needs to be reflected to the main memory or low level cache. Okay. So we need to distinguish these two cases. Okay. So updated case and not updated case. Okay. So cache also includes some is a flag bit that indicates the updated cash flow. So this black bit is called the dirty bit. So dirty bit means that the cache has the block, and then this block is updated by write operation. So this block is different from the block in the main memory. So and then it is called the this block is dirty. Okay. And then if the dirty bit is set, so which means that dirty is 1, so which means that this block is updated. So whether this block is deleted from the cache, and this block is written to the lower level cache or main memory. So this is the write back cache. Okay. This is write back cache. So also if you read the CPU specification, you can find the cache is employed in the CPU, and usually the most processor employs write back cache. Okay. So this is the write case, which means that in the write latest is given the target data is found in the cache. But we can also think about the write miss case. Okay. So here, so for the write hit case, there can be two cases: write do and then write back. Okay. But we also need to consider write miss case. So what is the write miss? So write miss means it's just store A, some address A. The store instruction is executed, and then we check the cache. Okay. But the target data is not found in the cache. So what should we do? So this is just the store instruction, right? And then by definition, the store instruction needs to update the main memory, right? So the first possible operation is that, we just bypass the cache, okay? Because the cache does not have any target data in the block. So bypass the cache, and then this data is stored in the main memory or main memory, okay? So this is called the write around, okay? And then another choice is, this is the miss. And then we can just handle this case like the read miss. Okay, so it's a miss. Then so this is the we can handle this case like the normal miss case. So it's a miss by load instruction. Then request the entire block. Request the entire block from the main memory, and then allocate the cache block using this requested block. Okay. Then update the data in this block. So allocate on miss means that, so this is called the allocate on miss. Okay. So which means in the write miss case, then the cache block is newly allocated. Okay. Then the block is updated. So it's very similar to the write back. Okay. So write back cache actually use the allocate on miss policy. Okay. So this is the write miss case for the cache. So write operation is actually, so write operation is a little bit complex, or it means a little bit tricky compared to the read operation. Actually, it's same for the computer system and program. Okay, because write updates the main write needs to update the memory. Okay, but read just we get so the read operation does not modify the data, right? So that's why the write operation is the more complex. Okay, so this is some example of the other cache, and then this cache. So actually, it's the same, but also you can find some different organization stuff. So which means that one cache block has the multiple bytes. So it's a large cache block. Okay, so I will skip here. Let's skip here. Okay, then let's think about the performance of cache. Okay, so why do you use cache? The purpose of cache is to reduce the data fetch latency. So it means that when the load instruction is executed and the data is requested from the main memory, then we want to reduce this latency. Okay? Then in order to reduce the latency from the main memory, we use cache. And then also I mentioned that when the data is requested from the cache, the data is requested to the cache, then there are two cases, it's a hit and miss. Okay. Then, so actually, let's focus on the Aeron cache. In chapter 4, so we learned about the process architecture, and then I also mentioned that actually the data memory or instruction memories are Aeron caches, right? So when we discussed about the process architecture, we assume that when the data is requested to the memory, so it's an instruction memory or data memory, actually instruction cache and data cache, we assume that the data is always found, okay? Which means it's hit. So usually we assume that when the data exists in Aeron cache, then the data can be immediately read from this data memory or instruction memory. Okay? So actually hit case does not waste the clock cycles. Okay, so we assume that we can read data from this memory, like Aeron cache, Aeron instruction cache, or Aeron data cache within one clock. But actually, it's not true in the modern CPU. So it is because now we use the very fast clock in the modern CPU, so it can take multiple cycles. But in this course, we assume that for the hit case, then we can read the data within one clock. Okay, so for this hit case, we do not waste clock cycles. Now, how about the miss? So this is the cache, and then this is some request. So when the request is given, then the cache is checked. Okay. Then if the data is found, the data is given. How about the miss case? For the miss case, the cache also needs to be checked. Okay. So which means that miss also includes the same process. So which means that we need to check. We need to check the cache. So which means that we need to compare the path in the cache. The same process is required. So actually, when we consider the required cycles for cache miss, the cache miss cycle, so these required cycles include the cycles for check cache, okay, and then miss penalty. Okay, and then actually this is common. This is same to the cache hit case. Okay, this is the hit case, same to the hit case, because for the hit case we also need to check the cache. Okay, so the additional cycles, additionally wasted cycles by a cache miss is miss penalty. Okay, so we can need to understand. Okay, so in the hit case, the plan is not wasted because it's the same to the as we learned in the chapter 4. But in the miss, this is same to the hit, like hit cycle, so it's not wasted, but the miss penalty is added. Okay, so this is the wasted cycles by a cache miss. So we can calculate the wasted cycles by cache miss like this. Okay, so we can count the number of instructions. This is the IC actually. This is the instruction count, and then also we can measure the number of misses per instruction. Okay, so and then miss penalty. Then this is the wasted cycles by cache. Okay, so how can we reduce? How can we improve the performance? So actually we cannot modify instruction count because this is the software area. And then also we cannot modify miss penalty. So we need to reduce the number of misses per instruction. Okay. So this is the example. So let us assume that the instruction cache miss rate is the 2%, then the miss rate of the data cache is the 4%, and then miss penalty is the 100 cycles. So which means that this is the wasted cycles by cache miss. And then base CPI, so is the ideal. So base CPI is the 2. So which means that for the ideal cache, the base CPI is 2. So which means that if the miss rate is 0%, so every cache request is hit, then the base CPI is 2%. And then why this information is required? Because processor has the instruction cache and data cache, and then when do we use instruction cache? Actually, every instruction requires to access instruction cache. Why? Because we need to fetch instruction from the instruction cache. Okay. So actually, every instruction needs to access instruction cache. So which means that the 100% of instruction access instruction cache. But how about the data cache? The data cache is accessed by load and store instructions only, right? So that's why we require this information. So load and stores occupies 36% of instruction. Then how can we calculate the wasted cycles by cache? So I mentioned that the instruction cache, the cache miss rate is the 2%. So which means that the two instructions per 100, two instructions for every 100 instruction is listed in the instruction cache. That's just the miss rate is the 2%. Okay. Then this is the miss penalty. Okay. So which means with this rate, the wasted cycle by instruction cache miss is the 2 cycles. Okay, because this is miss penalty and miss happen, and then this is the miss rate, the percentage of cache miss. How about the Tcache? Tcache is accessed by load and store instruction, right? So actually we need to use the percentage of load and store instruction. Okay, and then what is the miss rate? Miss rate is the 4%. Then the miss penalty is the same. So 1.44 is the wasted cycles, the average wasted cycles by data cache miss. So what is the CPI? CPI is the 5.44. So if we just consider the cache miss rate, then ideal CPU, the CPI of the ideal CPU is 2, and then CPI of the real cache is the 5.44. So this is the 2.72. So which means that ideal CPU is 2.72 times that. That's the, okay. So amazing, right? So you can think that this rate 2% is very low, right? So which means that most of instructions can be found in the cache. But even though this rate is very low, the cache, but the wasted cycles by cache miss is rather high compared to the base CPI, right? Base CPI is 2. Usually we assume that the base CPI is 1, but in this example, we assume the base CPI is 2 for instruction. So even though base CPI is high, if we just consider the cache, the real cache, then the computer performance is degraded significantly, very significantly, right? Nearly 3 times slower than the ideal CPU. Okay, so that's why the cache performance is critical for the performance of an entire processor. Okay, so then we can define another cache performance metric called the average memory access time. Okay, so this is some metrics for indicating the performance of cache. Okay, so average, we can calculate the average memory access time of the cache like this. This is the hit time plus miss rate multiplied by miss penalty. Okay, so as I mentioned, when the cache is checked, the hit time is taken. Okay, so which means that we need to check the cache for the request, for the incoming request. And then this is the additional time by a miss. Okay, so using the hit time plus this is the base time, and then this is the additional time for the miss case. So this is called so if we just add the miss rate multiplied by miss penalty, then this is called the average memory access time. So average memory access time is that when we access the memory, then we can measure the access time. So average memory access time is the average time for accessing memory. Okay, so we can calculate. This is the example. Okay, and then so we can calculate the average memory access time like this. But if in this example, you can observe, heat time is represented as the cycle. Okay? So it is because for the heat case, we can just consume one cycle. Okay? So even though this memory is very fast. Clock cycle is the 1 nanosecond, but the heat time is the 0.2 nanosecond. So you may think that we can use this information for the heat time, but it's not true because for the heat case, even though the heat time is much lower than this clock period, when we access the memory, the cache, then we consume one cycle. So that's why the heat time is represented as the cycle. Okay. So in the miss penalty is the 20 cycle, then miss rate is here, and AMAT is the 2 nanoseconds. This is average memory access time. So this is called the AMAT. So we can also use this average access time. So actually this is very good for the exam question. Okay. So then how can so what is required for increasing the performance of cache? So if we just check this AMAT, average memory access time, then the average memory access time is composed of heat time plus miss rate multiplied by miss penalty. So which means if we can reduce the AMAT, then we can improve the performance of the cache, right? How can we improve the performance? We need to reduce the AMAT. So we can reduce the heat time. Okay, this is also very important. If the heat time is long, then the AMAT is also increased. So in this case, then so more cycles can be wasted because of the memory accesses. Okay, so and then we need to reduce the missed rate. Okay, also we need to reduce the miss penalty. Okay, so these factors are critical for the performance of cache. Okay. Then let's discuss about the associative cache. Okay, so this is the some you can not okay. So okay, so what is the associative cache? So why? So let's think about this. So firstly, we learned about the direct mapped cache. Right? What is the direct mapped cache? The part of address, the lower part of address is used as the index of the cache. Okay, so this is the example of direct mapped cache. So actually for this cache block, only these blocks can be stored in this cache block. Okay, so this is the direct mapped cache. Then what can be the problem with this direct mapped cache? The problem said, firstly, so this is the A, this is B, this is C, and this is D. So in the worst case, let us assume that we execute the load word A first, then it will be missed in the cache because there is no data in the cache firstly. So this is missed. And then load order B. And then in the direct mapped cache, this B is here. Then B also needs to be stored in this block. What's the problem? This block was already occupied by A. So in this case, A needs to be evicted from the cache, and then B is duly allocated. And then after that, so load C, B is evicted, and then C is duly allocated. That's the problem. Problem is, this cache has the 8 blocks, right? But for this worst case, only 1 block is used again and again. So which means, even though this cache has empty blocks, these empty blocks are not used. Okay? Only because only this block is used for this A, B, C, D. Okay? So which means the miss is cache misses are caused by some direct mapping mechanism. Okay, so this can be the problem. So this is just the worst case, right? This is the worst case, but we can also imagine this case. So how can we solve this situation, this problem? So there are empty slots. So there are empty blocks in the cache. Then regarding this cache index, we can store any data, any empty blocks in the cache. That can be possible, right? We can just distinguish, we can just identify the requested block address in the cache. And that's it, right? So in this case, so we can just compare the address of the block using some stored address in the cache. Okay. So fully associative cache means that this cache do not use index from the address. Okay. So in the direct mapped cache, then we use the index of the direct mapped cache from the lower part of the address field. Okay, but if we map the cache index like this, then the cache, so even though the cache has the empty slot, then these empty slots are not used. So this is the resources wasted. Resources are wasted. So fully associative cache means that we can store newly allocated block to any empty blocks in the cache. Okay, this is the fully associative cache. That was the problem. So this is good, right? The performance can be improved, right? So I mentioned that in the worst case, the cache miss happens again and again. So it means that the bit rate can be increased by this case. The worst case. But if we use the fully associative cache, then we can reduce the cache miss rate, right? But there are no free. How can I say? There are no free deals in the world. Okay. So problem is the cost is high. Okay. So we can find the comparator per entry. So it's expensive. So why? So if you see the structure of the direct net cash, so this is the structure of the direct net cash. The firstly, the target cash index is decided by the this address field, right? Then the tag is compared with the so this tag stored in the cash block is compared with the tag in this address field. Okay, so which means that we need to use the one comparator. Okay. Then how about the fully associative cache? Fully associative cache does not have this part, okay? Because the data can be stored in any empty block, so any blocks. What does that mean? Oh, actually, these are all tagged. And then for this case, we don't know the block, so this address block is, we don't know the place, the target index of this cache. So which means that actually we need to compare tags stored, all tags stored in the, do you understand? Because we don't know the target index, okay? Because the index is not included in the address field, which means that all these address fields, remaining fields, address fields need to be used as the tag, and then we don't know the target location, the cache. So which means we need to compare all tags in the cache using this tag. Okay, so if we use the direct net cache, we just require one comparator. But in this case, we require, so this is cache at the 1024 blocks, which means we require 1024 comparators for the fully associatable cache. Okay, so it's expensive. Okay, the comparator is also the hardware logic. So it means that not to implement the fully associatable cache, then we need to use many comparators. Okay, so this is not good. Then we also need to consider the cost. So we can select some intermediate approach. So it's a kind of some 중립적인, 중립한데 중도적인 the intermediate approach. So called the set associative cache. Okay, and then also you can find the n. So it's some kind of a number. So n way set associative cache. So n way set associative cache means that this is the cache index. And then this is a certain set indexed by address index field in the address, but this set can include the multiple blocks. Okay, so this is the block 1, block 0, because we are incorporating by block 1, block 2, block 3. Okay, then so we can use this index. We can use this index from the certain field of the address, like the direct map cache. But the different thing is that in the one set, this is the one set. This one set can include multiple blocks. So direct map cache means that and the cache index is determined by the address field, then only one block can be stored. Okay, but the n way set associated with cache, the when a way set associated with cache, n blocks can be stored in the is set n way set associated with cache. Okay, so n way set associated with cache requires the n comparators. So what does that mean? So if the index is decided from the address field, then we just check this target set. But target set includes the n blocks. Then we just compare n tags stored in these n blocks in the target set. Okay, so this is the n way set associated with cache. So this is, I mentioned this is the intermediate approach. So which means that we can just use the n comparators instead of the large number of comparators. But we can also store multiple blocks to the target set. Okay. So for example, if we can store 4 blocks per set, then this is for this case, A, B, C, D, then we can store A, B, C, D in the cache. Okay, A is not even given. Okay, do you understand? So this is just the example. Okay, let us assume that the cache has the total A blocks. So which means that the size of the cache is the same for this direct mapped cache and set associative cache and fully associative cache. So this is the two-way set associative cache. So in the direct mapped cache, there are 8 blocks here. So actually number of blocks are the same. Okay, number of blocks is the same. But when the index is determined, then we can only one cache block can be stored in this index, this set. Okay, so this is the direct mapped cache. So we need to compare only one cache for the direct mapped cache. But how about the set associative cache? So in this example, we just set index is determined from the address field. Okay, address field. Then if for the set index is determined, then there is on one set includes 2 blocks. So we can just compare 2 tags in this case. The fully associative cache, then the block can be stored in any block. So we need to compare every block, every tag in the cache. Okay, so this is just so the direct mapped cache, set associative cache, and fully associative cache. Okay, so actually, we can say that direct mapped cache is the one-way set associated with the cache because only one block is stored in the one set. So this is some structure of the direct mapped cache for the 8 entries, 8 blocks. Okay, so the direct mapped cache for the one set stores the one tag and one data block. The two-way set associative cache for the one set, and we can just store 2 tags and then 2 data blocks. Then 4. Okay. So, what can you observe? Because the size of cache is the same, because the cache size is also a kind of hardware resources, because the cache size is the same, then the number of sets is change. Okay, so direct method cache has the A set. Okay, and then two-way set associated cache includes the O set. Okay, so because this direct method cache has the A set, then we need to use the 3 bits for the index bit of the cache, right? But the two-way set associated cache has the 4 set, so we need to use the 2 bits as the set index of this two-way set associated cache. Okay. Okay, so let's compare the performance using the example. Okay. So we will just compare the direct mapped cache and then two-way set associative cache and fully associative cache. And then let us assume that these caches include 4 blocks per cache. Okay, the cache includes the 4 blocks, so which means that we can store 4 blocks in the cache. Okay, but we can organize the cache as the direct mapped cache, so which means that this cache has the 4 set. The two-way set associative cache, so which means we can store this cache has the 2 sets. Okay, the fully associative cache, so which means that we can store any place or any blocks over this fully associated cache. And then this is the block access sequence. So firstly, 0 is requested and 8 is requested, 0, 6, 8. Okay, for the direct mapped cache, so this is the block address. So, and then this direct mapped cache has the 4 sets, right? So we need to use the 2 bits as the index of the cache, right? So this is the 0, 0, 0, and then 8 is the 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 0. So for this block address, we use the last 2 bits as the index of the cache, right? You understand? Okay. Okay. So this is the cache index. So this is 0 because we use the last two bits. So 0, 0, 0, 2, 0. However, so in this case, because the cache index is 0, then we need to access the cache index 0 here. It's this, right? Because there is no data. 8. This is also miss. Why? Because this is new data, 8. And then, but problem is that this data is evicted from the cache because cache index is 0, so this data needs to be stored in 0, cache index 0, and cache index 0. Okay, you understand? And then 0. Because this block is already evicted from the cache, we cannot find this block in the cache. So still this. What's the problem? We can observe temporal locality here, right? Because 0 is accessed and then 0 is accessed again. It's a temporal locality. But because we use the direct mapped cache, this temporal locality is not exploited by cache. Because this is evicted, already evicted. Okay? So this again, so here, 6, cache index is 2, is stored here. And then another 8. So target index is 0. But problem is, this is also evicted. But is not found in the cache, also this is missed. So we can find temporal locality here, and then temporal locality here, A. But temporal locality is not utilized in the cache, in the direct cache, because of 0 and 8 is pointing the same cache index in the direct cache. And how about the two-way set associative cache? Two-way set associative cache. So one set includes the two cache blocks, right? So, and then there are, in this example, there are total 4 blocks. So this cache has the two sets. Okay, so which means we can use the 1 bit as the cache set index. Is the set index. So 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0. So for this block address, we use the one bit, the last bit. So we can use this bit as the set index. Okay. So this is the set index. Okay. 0, 0, 0, all zeros, because as you can see, the LSB is the LSB of these block address are all zeros. How about the 0? It's a miss because there are no data in the cache initially. 8. This is also miss. This is the first access. What is different? So as you can see, the block address 0 and block address 8 use the same set index 0, but set 0 has the two available blocks, right? So the mem0 can be stored here, and then after that 8 is here, then 8 can be stored in the empty blocks in the target set. Okay, so we can find that a mem0 is not evicted. So in the direct mem cache, mem0 is evicted. Okay, so it means what we can store the mem8. 0, this is hit because we can find mem0 in the target set. 6. So we need to, so 6 is also targeting index 0. So which means, so but the target set is already occupied by two valid blocks, right? So which means that we need to evaluate one of these blocks. Which block? So there can be several, we can apply some different policies, but we frequently use the LRU, the list LRU means the list recently used. List recently used. What does that mean? List recently used. So the old, how can I say? Meaning so old data, but this old data is so of the accepted long time ago. Okay, list recently used means that accessed longer time ago. Okay, so what is the list recently data? mem0 or mem8? mem8, because mem0 is accessed by this one. Okay, so this is the recently used, right? mem0 is recently used, and then mem8 is the least recently used. Okay, do you understand? So in this case, MEM8 is evicted. So based on this policy, MEM8 is evicted from the cache. So MEM6 is allocated. So in this case, A is here, A is not found in the cache because A is evicted already. So it's a miss. So temporal locality is here, but we can observe temporal locality here, but it's not utilized. But we can observe that the block address 0 is the temporal locality of this case is utilized in the two-way set associative cache. Fully associative cache does not have any index because the data can be stored in any empty slot. So 0 here, the miss because there are no data. A miss is stored here. 0 is a hit, right? Because it's here. 6 is a miss, but 6 can be stored in the empty block. 8 hit. Okay. So this is the fully associative cache. So this is very simple example, but if using this simple example, we can find that for the direct method cache, the miss rate is the 100%. Okay. How about the two-way set associative cache? The miss rate is the 80%. Fully associative cache, the miss rate is the 60%. So which means if we use the fully associative cache, then you can reduce the cache miss rate. But how much? So this is for some imaginary example, right? So this example is designed for education, okay, for teaching. But how much? So this is the some simulation data, and then if we use this is let us we assume that the data cache size is the 64 kilobyte. Then we run the spec 2000 benchmark, and then this is the miss rate. So if we use the 1A set associative cache, the miss rate is the 10%. It's the direct method cache. Direct method cache. 2A 8.6, 4A 8.3, 8.8A 8.1. So we can observe that if we use the direct method cache, the miss rate is rather high. But if we use the two-way or four-way or eight-way, the miss rate is reduced, but slightly reduced. Okay. So the graph looks like this. Okay. So which means that we don't need to use the fully associative cache because the miss rate is saturated by some point of the associativity. So we can use if the miss rate is saturated for a certain point, then we don't need to use the fully associative cache. Okay. So it's okay to use the 4-way or 8-way set associative cache. So if you read some CPU specification document, you can find the associativity. So this is called the associativity. You can find the associativity of the cache. Okay? And you can find that the modern CPU use the 8-way or 4-way. 4-way for the L1 or 8-way or 16-way for the L2 or L3. Okay? So CPUs do not use fully associated. It's so expensive. But the cache miss rate is saturated by associated. Okay? So this is the example of the set associative cache. So what is the associativity of this cache? So you can find the four comparators. So associative is four. So this is the four-way set associative cache. Okay. And then as you can see, so this is the set index. Okay. So compared to the direct mapped cache, the index, the number of sets is reduced. So it was the 1024 and it will reduce to the 256 because one set includes the four blocks. Okay. And question: three-way is possible? So this is 4-way. Three-way is possible. Three-way is also possible, right? Because you can just remove this part, but you can use the set index for this three-way set associated with cache. Okay. So also I also explained about the replacement policy. So we frequently use the least recently used policy. Okay. Or sometimes you can use the random policy. Okay. Okay, so I will stop here. Then the next class I will normalize the cache, and then we will learn about double dynamic. Any question? Okay, thank you for your attention. See you in the next class.